I have 27 students here, but I only have 1, 2, 3, 4, 5, 6, 12. 12 of you show up on video. Can the rest of the students show up as well? I want to see if conference can handle everyone. That's the main concern. Rumor says that I cannot use it for it will crash or whatever. 14.
Can you see those students right now?
Yes, I can see 1, 2, 3, 4, 5, 6, 7, 8, 16 students.
Okay, because I thought we can look at other students too, but I don't see anyone here on my screen.
Oh, really? You cannot see other students?
No.
I only see you.
We can see it.
That's interesting.
I think we only see ourselves and you.
Yeah.
Yes, Professor. That is weird. Audio alert for chat. That's interesting. How come? Oh well, that's okay. So let me see how many people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 19 students on my screen. It's okay. Okay, but for the rest of students, I hope you can hear and see me on the screen. I was trying to do the brick room. Let me see if I can do brick room. 28 students now. 28 students. Well, what do I need to say? Well, it is a complicated situation. I was in the faculty meeting on Monday. I basically asked everyone, what about the lab? They said that, oh, we don't know. So none of the faculty in the life science department knows what to do about the lab. So for those of you who cannot see, look at the icon here. You see there's a camera icon. This camera icon, you click on it, then you should activate it. Yes, or turn on your webcam from your setting. Okay. Let me see. It has a little bit lag. Okay, how about this? Everyone mute your microphone. A lot of noise. So you mute it by clicking the microphone button once. All right, thank you. Your Kwan is very dark. It's okay. Anyway, yeah, I asked. Well, restart your computer. Okay, I asked student, asked the department. They said that they don't know what to do. So I'll ask them again on Wednesday, see how it goes. Regarding to the lab quiz, that can be easily solved. Lab quiz, I can give you to do the lab quiz online. That means on Canvas. But to do that, you need to do something called, you need to use Google Chrome. My handwriting looks so bad. Why is it like that? About this. Google Chrome. Okay, much better. It's still lag. The lag is due to the internet. Maybe I should go to school to use the school's internet, Google Chrome. And you need to download an extension called Pretoria. Maybe I should email you guys about this so that I can type better. Pretoria. Pretoria, yeah. In this case, theoretically, I can even let you take the lecture exam. But I'll see how the department feel about this, giving you guys the exam online using Proctorial and stuff. But the lab quiz is kind of informal, so lab quiz I can decide myself. I can let you guys take it on Canvas and on Proctorial. But the bottom line is that the lab, we still don't know what to do with the lab. I'll bug them again on Wednesday. Hopefully, I can get back to you with some positive news. I should email you about this. Oh, it's okay. Okay, now so if you want to talk, you can unmute it. If is there any question? No. Okay. Then let's start. Okay, I want to know how many of you, let me see. Oh, there's no hand raising button. Maybe I should do this pool. Okay, pool. Start a pool. So how many of you have finished? Don't press yes. I haven't even asked the question. Yes. Why do you guys are yes people? How many of you have finished watching all 3 videos? Oh, 30 students. All 30 students are here. That's good. So let me see. 27 students voted. Oh no, 29 students are here. Only 29 students. Someone dropped. So 27 voted. I need 2 more students to vote. Okay, so far 15 students said yes, they finished watching all the video. 1 more student need to vote. 1 more student need to vote. 13 students said no. Okay. The things is that I would strongly encourage you guys to watch all the video now. You remember last week I told you that, I'm not supposed to give you the lecture video because it is not an online class, it's not a hybrid class. I have to teach. But now the situation is different. Everything is now online. So it is legal for me to tell you, okay, watch the video, learn it yourself, okay? So for the 13 or 14 students, 1 student didn't vote. For the 13 students that you said no, okay, please finish watching all 3 videos. Yes, right now we are online class, so you should watch it. And then so that yeah, I will see how you guys feel about this. So Melanie, you're here.
Yeah.
Okay, good. So yeah, for the rest of the 13 students, please watch. That's it. So I assume you learn a little bit about the what's that called? I assume you learned the Okay, since not everyone watched the all free video, then I have to give you a brief review as a responsible person. Oh, by the way, the exam. Oh, yeah, regarding the exam. Okay, I hate to say this. I'll finish grading it tonight. Okay, I only have 2 more questions to grade. Then I'll be able to do that. I only have 2 more questions to do, and then I'll be able to do it. Yeah. Yes. How there's so much sound here. Someone is trying to activate it. Or okay, let me see if I can share my screen. If I can share the screen. Application window, share application window, big blue button, share. Can you see my screen?
Yes.
All right. Oh, okay, good. I heard 1 yes. So this is basically this is the last video. Okay. Last time in the class we talked about hyperpolarization, depolarization, and repolarization. These 3 terms of definition. Now I want you to look at this picture. This picture tells you the graded membrane potential. So graded membrane potential, the first thing is that I want you guys to oh, yeah, I cannot do this. I cannot write on this. This is not too cool. I cannot write on this. Stop sharing. Stop sharing. But you can, how do I do that? What is the best way to do it? I show you here. If I show you the screen, then I won't be able to. Oh, okay. Let me try this, see if it works. Okay, share this, upload presentation. Oh, I can do that. That's nice. Okay. Let me hurry. Let me show you the video. Because if I don't talk about the graded membrane potential, if I talk about action potential, you guys won't be able to understand it. That would be disastrous. Oh, yeah. Why is it so lame? Sorry, I need to wait for my drive to run. No, not this one. Okay, here. 6 physiology. Okay. Nervous system 1. Okay. No. Okay, it's kind of work. So the PDF file is here. Okay, we can take a look. Okay, good. This one. This is the one. Okay, perfect. Okay, perfect. Now, so as you can see on the screen, This is the graded membrane potential. So what is graded? We learn about resting membrane potential. Now we learn about the graded membrane potential. Now theoretically, you have already watched the
I
video.
can't see anything.
You cannot see anything. How
No.
many of you
Anything
How many
either.
of you cannot see it?
I can't see anything either.
It just popped up, but we weren't able to see it.
No, I still can't see anything.
I still can't see anything.
Is it
Maybe-
is it just a graph?
It's white.
It is figure 8.15.
Oh, I
Yeah.
see it now. Okay.
It takes time to load. I guess it takes time to load because the web traffic, the internet, not everyone is that fast, especially mine, I guess. I'm using the free internet from the lounge in my place. How many of you still cannot see it? Just voice.
I can see the depolarization, hyperpolarization.
Okay, good. So you can see the figure 8.15, Molly, right, Molly?
Mm-hmm. Yeah.
Good. Thank you. Okay. Assume since no one voiced their frustration not seeing this, I assume you all see this now. Okay. What I want to show you is this one. Okay. So depolarization. What is the stimulus? Stimulus, you can assume that it is a mild electric shock. A mild electric shock. When you give a mild electric shock to a neuron, the neuron will have a upward deflection.
But doesn't it have to go above a certain amount of millivolts for it to be
That's a
registered
good
as
question.
something?
That's a good question. Yes. When it is not above that threshold, then we call it greater potential. Okay, we'll talk about step by step. I assume you have done your study, which is very impressive, but we go by step because many students, they haven't watched the video, and that's why it is redundant, okay? So when you give a mild electric shock, you give a upward deflection of the membrane potential. That means it will make the membrane potential relatively more positive. Then we call this depolarization. If you look at the definition from last week, it is depolarization. Sometimes we will get hyperpolarization, meaning that the downward deflection, we call that hyperpolarization, meaning that it is making it more negative or decreasing the membrane potential even more. So you may ask, Professor, how come you give the mild electric shock? How come you will give depolarization and sometimes you will give hyperpolarization? How come? Well, the main reason is that for mild electric shock, you can actually change the polarity of the mild electric shock. You can make the electric shock positive. You can make the electric shock negative. When you change the polarity of the electric shock, then you can induce either depolarization or hyperpolarization. And this slight upward deflection or downward deflection, we call it graded membrane potential. So these two, we both call it graded membrane potential. They are like the mild deflection or mild disturbance of the resting membrane potential. Have I told you that the analogy of the resting membrane potential is like homeostasis. Resting membrane potential is like homeostasis. When we give a mild electric shock to produce a graded membrane potential, it's like we're disturbing the homeostasis. But the disturbance is minor. That's why we call it graded membrane potential. But let me give you a preview based on what Molly told us. Can anyone heard what Molly said previously? All right. Okay, whatever. So Molly said that isn't that if it go higher than certain threshold, then something will happen. I said yes. So when the amplitude of this greater membrane potential is higher than certain threshold, then you will trigger action potential. So in other words, the disturbance or the disturbing the homeostasis has to be really large in order to cause action potential. To put it in a simple way, greater membrane potential and action potential, you may call it, they are not in a homeostasis. Yeah, they are the disturbance of the homeostatic level in the neuron. It's just that greater membrane potential is a minor. It's like a cold or flu. Okay, action potential is like coronavirus, COVID-19. Okay, the very serious one. No, I think that's a good analogy for today. So yeah, that's why I said that greater membrane potential is like English words. Action potential is like the sentence. So now we learn the English word first. There are properties of the greater membrane potential. So where can I write it? So the lecture note you should write a lecture note somewhere on your notebook and put down figure 8.15. So it is the properties. Ooh, the lag is really serious. The internet lag. Maybe I should go back to school to teach. Yes, school has a faster internet than this one. Properties of. So greater membrane potential, I'm not going to spell it out, but I only put it GP. GP is the shorthand for greater membrane potential. Yeah, some people just simply say greater potential. So greater membrane potential is the same as greater potential. And I just call it GP. So the first properties is this one, B part here. The first property is B. GP. Okay, many students call, oh, this is a fish symbol, a fish symbol. This is called proportional to the stimulus intensity. Oh, my pen. I understand why it doesn't go. The internet speed is too slow at my lounge. So I think next time I'll go back to school to teach you guys. Yes, I can do that. I sneak into the school. There is a office. There's a room that has no one there. No one uses it. Now the school is so quiet. Internet will be very fast. That it will be the best way to teach. Okay. Property number 1. Greater potential is the fish is called proportional. Right now, when I put stimulus intensity like that, then we call it directly proportional. Greater potential is directly proportional to the stimulus intensity. What does it mean? Directly proportional. Well, let's take a look. If we have weak stimulus, then we have a small deflection. Let's say we just use the upward deflection. Let's just say we use the depolarization. But if we have a stronger electric shock, then the amplitude of the greater potential, the GP, will be higher. The amplitude will be higher. In other words, if you give an even stronger stimulus, what will happen to the greater potential? The greater potential will even get even higher. So it can be like that. So that's what we call we call this a graded response. If you look at the original PDF file, I said a graded membrane potential. The reason we call it graded membrane potential, graded is the opposite of digital. It is like analog. Greater is similar to analog, okay? Meaning that the amplitude of the greater potential is directly proportional to the stimulus intensity, meaning that the stronger the stimulus, the higher the amplitude. The weaker the stimulus, the lower the amplitude. We call this graded response. Graded response. What is the opposite of graded response? You may or may not have heard about this. The opposite of graded response is called all or none. All or none. It's like digital. You know, whenever we call digital, digital photo frame, digital, everything is digital. Digital meaning it is 0 or 1, 0 or 1, 1 or 0. So all or none is the opposite of graded response. You either have it or don't have it. We call it all or none. Graded response meaning that it will change according to the stimulus strength. Okay, so this is property number 1. Property number 2. It is this one here. Property number 2, GP, graded potential. Again, the fish meaning proportional. But this time it is not directly proportional. It is inversely proportional. What do you mean inversely? It is 1 over. I hope you remember your high school math. 1 over, what is that distance? It is not responding. The internet is so slow. Distance. Now it is much smoother. Good job. Nice handwriting. Slowly, slowly, and steady. Okay. Distance. Okay. So it is graded potential is inversely proportional to distance. What do I mean by distance? Okay. Let's take a look here. Well, again, okay, we have a mild electric shock at the arrow here, and then we trigger a depolarization, a small graded potential. Okay, and then from here to here, it is approximately 1 millimeter. You can assume that although in here it said that the x-axis should be time, x-axis is time here, but for the panel C here, the x-axis is actually distance. This one is actually distance. Ooh. Yeah, distance. You may assume what do you mean distance? You may assume that the stimulus, with the mild electric shock we give here, it is at the one end of the axon. Okay, you may assume that it is at one end of the axon. When we give a mild electric shock here at one end of the axon, we get a small deflection called depolarization or graded potential, and then this graded potential will travel along the axon. As it moves along the axon, and then we record the response. Remember recording, we put a voltmeter, the recording electrode, into the cell. And then we poke the recording electrode 1 millimeter after the site of the stimulus at the axon. And then we measure the response of the graded potential. As you can see that it is a lot smaller. Okay. And what if we measure the response 1 millimeter later? 1 millimeter. Take a guess. What will happen? Someone, if you know the answer, you can yell out the answer. Although I cannot see your face because I'm in full screen mode.
It'll get smaller.
Yes, you get even smaller. It will actually disappear. So you become a flat line. Hey, who answered this question?
Amanda.
Amanda. Oh, good job, Amanda. See,
Just
now you are more responsive. In the classroom, you sit at the back. You don't feel like answering questions, but on the internet, because you're at home, then you feel like you are answering questions. It is exactly the same. I hate to say this. I sound like a internet predator. Okay, so what happened is that internet predator take advantage of young girls. Like Amanda. Okay, oh, you are chatting at home, and then you feel safe. That's why you are more open to talk. And then when you get to know him better, when you feel more comfortable with him, then he'll ask you to meet up with him, something like that. It's the same idea. When we are doing this online teaching, many of you are at home, you feel comfortable, so many of you will start to speak, will start to talk, which is a good thing. Anyway, I'm not an internet predator, I'm just your professor. This is a very bad analogy. Well, you know that I always say something stupid like that. Okay, the key point for this is that the graded membrane potential decreases according to the distance. Decreases according to the distance, okay? The longer the distance, the smaller the amplitude. This is what we call inversely proportional. Inversely proportional. The shorter the distance, the higher the amplitude. This is what we call inversely proportional. What is a special term for that? We call it decremental. Not Sacramento, not our California capital. Decremental response. Decremental response, meaning that the graded potential will die. Okay, it will die. Okay, it will disappear. It is not a very weak depolarization. That's why. Now the third property, we only have 3 properties. Don't worry. I know that I'm cramping all my notes on this figure, which is not very good. Don't worry about this. I guess at least you can copy it because I write very slow because of the lagging. You may probably know the summation. Summation, okay. Summation, we have 2 types, temporal and spatial, okay. We see it here, temporal and spatial. Temporal, meaning that
Means time?
time, yeah, temporal means time. Excellent, good job. Now we have, let's see if we can magnify bigger. Oh, we can, that's good. Is that the maximum? I like this, I can make it very big. Oh, nice. Can I make it even bigger? This is so nice. I like online teaching using conference. Okay, now you see this here. Okay, again, we have a weak electric shock to stimulate the neuron here. So we get a upward deflection, a greater potential, a depolarization here. Now, after a while, so now we go back to time. The x-axis is time. So after maybe a while, we give another stimulus. We wait for a little bit, then we give a stimulus here. This weak electric shock is the same as the first one, the black circle, okay? Because they are both X. That means they have the same stimulus intensity. That's why their amplitude is approximately the same. And theoretically, this one, the green X, it should look like this. Theoretically, okay, it should look like this. But guess what happened? Before the graded potential dies, we give another stimulus X, the same stimulus X, the same intensity. So we give the stimulus at the peak of the green one, of the first one, so that we induce another one, the purple one. Theoretically, it should be like this. But again, before it dies, what happened? We give a third stimulus at the peak of it, so that it goes like this. We build another one. So what it means is that the graded potential, if we stimulate the neuron fast enough, the key point is the timing. Just like someone said, I don't know who said that, time. If we stimulate them fast enough, that means the distance between them, the time between them, they are really short. So that the graded potential can build up on one another. The graded potential can build on one another. Then the overall amplitude can increase. If the amplitude here is 1 unit, 1 millivolt. This one, it is approximately 3. In other words, temporal submission has a very important function. It can increase the amplitude of the graded potential. The key point is the time. It has to be stimulated in a short time. Any questions so far before we move to the spatial submission? Any question? You just unmute yourself and ask me the question. I cannot see the chat. Right now I'm on full screen mode. Okay, now since you have no question, now let's take a look at the spatial summation. Spatial summation, as you remember, I have to draw my neuron. Okay, my funny neuron. Okay. My neuron is here. And then this is the axon terminal. Okay, now let's take a look. If we stimulate here, my thunderbolt doesn't look too good. We stimulate here. I call this dendrite X. This is dendrite X. Yes, I named the dendrite. Yes, it's like I'm naming my pet. If I give a mild electric shock at dendrite X, what will happen? I will get a graded potential. Am I right? I get a graded potential. The graded potential will travel this way to go into the soma. Now, how about now? I want to stimulate at dendrite Y here. Dendrite Y here. And then another thunderbolt. Oh, okay, good. And then I will get another action potential, not action, sorry, the graded potential. Come on, move. Okay. gradient potential, the purple one, and then you of course also go this way, go into the soma. I hope you know what soma is. Now, and then what happened when they meet at the soma? When they meet at the soma, they will combine. I would say they will add on each other. Then it will become higher. In other words, if the amplitude here is 1, I hate the lagging. It's 1 here because we use the same stimulus intensity. So the purple amplitude should also be 1. Should also be 1 here. And then the green amplitude will be 2. Because 1 plus 1 equals 2. So this is what it means on here that you see. This stimulus X is at the dendrite X. This stimulus Y is at dendrite Y. And then when they meet at the soma, the gradient potential from X and gradient potential from Y, they will add up and they will double the height of the gradient potential. Therefore, we call spatial summation. Spatial means space. Space. Yeah, temporal means the time. This is a space, time and space. This is time. Okay. Now, this is a question. For those of you who know the answer, unmute yourself, okay, and answer me this question. Let me see if I can come back to here. Okay, good. How many of you know that, okay, what are the three different ways the gradient potential can increase the height that you have learned? What are the 3 ways that the gradient potential can increase its height? If you know the answer, unmute yourself and yell your answer. It's just like in the classroom, you just yell your answer. You can unmute yourself and answer this question. Come on.
Isn't it a stronger stimulus?
Correct.
Closer time and closer space.
Okay.
Shorter distance.
You are good. You are good. I guess you're very close. Let's put it this way. The 3 ways to increase the stimulus. The 3 ways to increase the amplitude of the gradient potential or the height of the gradient potential. The first one is the stimulus intensity, meaning that let me decrease it so that you can see it. The stimulus intensity, stronger the stimulus intensity, the higher the peak. We call it graded response. Remember, we talked about this graded response. That is the one. So that's how we do this, the graded response. This is a property number 1. The first property, graded response. First one, it is direct proportional to stimulus intensity. So if you use a stronger electric shock, you make it higher, okay? And the other 2 ways, they are namely, we just talk about it, temporal summation and spatial summation. These 3 methods, they are the method that can increase the height or amplitude of the gradient potential. Why is it so important to know these 3 methods? When we talk about action potential right now, you will know why. So, is there any question so far? If you have a question, unmute yourself and yell out your question. Come on. So many people are chatting. Any question? Not many people are showing on the screen, even though I want to see your face. It's okay. It's good. People are helping each other. Not yet. Not yet. Proctoral, thank you. The great good, so I would like to know too. Go from website store. Okay, yes. Wow, you guys chat a lot. Jeez, you guys are listening to my lecture. Probably those people, they are the one that already watched my video. All right. Since you guys have no question, we will move to action potential. Yes, I'll teach you how to make a sentence. I'll teach you how to make sentence. Now the most important part. Let me see. Upload a presentation. I want this one to be active. Can you see a blank slide?
Yes, Professor.
Okay, can you see? Ooh. Can you see an action potential?
Yes.
Okay, good. I see some nodding. Someone said yes. Good. Before we go to action potential, we want to talk about some basic information. Okay. How do we get action potential? Molly at the beginning, she already gave us a preview. Oh, hey, I was wondering when some of you unmute and speak, can other people hear that? For example,
Yes.
okay, good. Jonathan answered my question, and then so everyone can hear his answer, right? That's good then. Okay, so you heard what Molly said at the beginning. Okay, isn't that, you're really higher, then there's something. Yes, this is what we call threshold. We'll talk about threshold later, but this is something that I want you to memorize. This is the action potential threshold. I should use blue, just to be consistent with my color scheme. Threshold. Okay, Thursday, I will go back to Glendale and teach you there. They have faster internet. Okay, they have faster internet. Threshold, action potential threshold. I want you to memorize this magic number minus -55 millivolt. Oh, really bad. The lagging of the internet is not good. All right. Action potential threshold minus 55. I want you to memorize this. Why is it so important? Well, remember, we just learned that, okay, there are 3 ways to increase the amplitude of the graded potential. One is that, okay, we do not give a mild electric shock, we give a strong electric shock. Then it will make it taller, higher. Or we can take advantage of spatial summation or temporal summation. All these 3 methods will give you a taller or higher graded potential. When the graded potential is as tall as minus 55, if the height or the amplitude of the graded potential is minus 55, then what will happen? Then it will transform like Sailor Moon. It will transform like Sailor Moon to become action potential. How many of you watch Sailor Moon? No one? Jeez, you guys are too young. Oh, one person, Shannon. Okay, we should talk. Okay, you're my good friend now. Someone public chat saying that, oh, your professor is crazy. Talk about Sailor Moon. Me, Lorenzo. Where are you? Why come you can yell at me on the screen, or you can show your face? Good, Lorenzo. Okay. The three of us can form a Sailor Moon Club on GCC. So remember, 555 is the threshold, so that greater potential will transform to become action potential. This is one of the background information. Another two background information I want you to know. Well, I hope you don't mind, but you basically get used to it already. What your professor like to say something politically incorrect all the time, and he doesn't care whether he gets fired or not. So this is something that I want to say. Let's talk about the properties of the two channels that we will talk about for this before we go to the action potential. It is also the background. Let's finish the background information, then we can take a 5 minutes break. It's almost 1 hour. So the first one we talk about, of course, our favorite voltage gated sodium channel. Remember on Thursday, I talked about we have 3 kinds of channel. The first kind is called lead channel. This is the second type of channel. We call this voltage gated ion channel. I give you an example, voltage gated sodium channel. And what is the other one I gave you? Voltage gated what? You can refer to your lecture note previously. What is the other one?
Chlor and potassium.
Correct, potassium. Susan, I saw that your speaker is light up, so I know that you are answering correctly. Correct. This is the potassium, okay? So we learned the properties, the background information, the threshold. Now we need to learn the properties or of these two channels as the background information before we learn about how greater potential transform into action potential. Let me go with this easy one. I always go with a difficult one that scare people. Voltage gated potassium channel is the easy one. Okay, it is easy because it's only 2 states. Okay. Close. And open. I hope you still remember what we learned at the beginning of semester. Membrane protein. Voltage gated potassium channel is a membrane protein, and it can be open or closed. And when it open, it will allow potassium ion, a charged particle, to go through the membrane. Because originally charged particle, they have charge, it will be repelled by the fatty acid chain, the hydrophobic non-polar fatty acid chain in the membrane. That's why they need a membrane protein to allow them to bypass the non-polar fatty acid chain. When it opens, then it can close. So it is very simple. Okay, voltage gated potassium channel can only open or close. But what makes it open? You may say that, you may ask, Professor, what makes it open? Okay, the name already tells you what makes it open. Voltage gated. What it means is that when there's a change in the membrane voltage, then this channel will open. When there's a change in the membrane voltage, then this channel will open. How can you change the membrane voltage, you may ask? Then very simple. Remember the example I gave you? Mild electric shock. When you have a mild electric shock, it changes the membrane potential, membrane voltage, membrane potential, then it will open this channel. It's just that simple. There is a different name for open. Open, you may call this Activate. We are. Yeah, I don't like this. The lagging. Thursday, I'll go back to GCC. I don't care if I get arrested or what. Activate. Hey, you guys know how to spell activate, right? Why don't you guys complete my spelling? Okay, the lagging, I hate the lagging. I can write faster, but I have to slow down. Activate. The first one is A, not D. It looks like D. This is an I. Close. There's another name. It's called deactivate. This is D. But good thing is that it's not crashing. I like that. Deactivate. I don't know. Maybe I heard another professor. She taught in Rio Hondo College, very east. It's like in Rio Hondo College. She said that the school internet is not good. It's so slow. A lot of so I'll see what happened on Thursday. So this is an easy one. What about sodium? Sodium is a little bit more complicated, just like women. They are kind of complicated. You have close. What? Crystal, you say something? Close. And of course, when you have close, of course you have open. This is really bad. And then guess what? There's a third state. We call it inactive. And then after inactivation, you close. Again, the same thing. Open is also known as activate. Close, also known as deactivate. And then you have inactivate state. Okay, that makes our life more complicated as a student. When you have to take an exam, you have to understand the differences. What is inactivate? Well, open and close, very simple. Open, ion can go through. Close, ion cannot go through. What about inactivate? Inactivate is basically the channel is open, but ion cannot go through. Yes, that's it. It is kind of like, yeah, I don't want to give this politically incorrect analogy. That would piss off many people. I'll get fired for sure. Okay, so anyway, this is what it means. Inactivate, the channel is open, but sodium ion cannot go through. So it is like in between. I know the analogy I want to give is the gender neutral bathroom, something like that. But you know, you got what I mean. But anyway, yeah. So yeah. So inactivate, the channel is open, but sodium ion cannot go through. When you close, then the channel is closed, so the ion cannot go through. When it is open, the channel is open, then sodium ion can go through. So what else? Let me finish up, then we take a break very quick. What's the difference? The political incorrect analogy for this one is that sodium is fast. What do I mean by fast? Sodium channel. They are fast to open, fast to inactivate, and fast to close. This potassium, they're slow. They're slow to open and then slow to close. The politically incorrect analogy is that voltage gated sodium channel is smart. Voltage gated potassium channel is stupid. Okay, remember this. It is stupid because everything is so slow. It is smart. It is very fast to respond. And there are two more properties of the sodium, because smart people, they have lots of issues, you know that. I don't know if you notice that smart people have lots of issues. Stupid people, you know, they're simple, they don't care about anything. Smart people, they have issues. So there are two issues. One is that sodium channel only go one way, clockwise. So it is another characteristic of smart people is that they're very stubborn. Why? Because they only go one way. They can only close, open, inactivate, close, open, inactivate, close, open, inactivate. They do not return. They do not go backward. This is how stubborn it is, which is another characteristic of smart people. They have issues because they are stubborn. And then the second property is that, okay, the cross means cannot skip. They cannot skip a state because they are stubborn. When they are closed, they cannot skip a state. They cannot skip open to become inactivate. When the channel is open, it cannot skip the inactivate state to become closed. When they are inactivate, they cannot skip the closed state to go directly into open. This is what I mean, cannot skip. If some of you really think about this, the two issues of this smart sodium channel 1 and 2, they are basically the same issue. What is the same issue? They are basically stem from the stubbornness, the same issue. When you think about it one way, it's basically, I'm saying that it cannot skip. Why? Because when you go backward, it is basically like skipping a step. I don't know if you can see that the two issues, they're basically the same issue, the same thing. It's just that we put it in a different way. Someone chat. Sorry, Professor, laptop died. Who said who died? Molly. Oh, it's okay. It's okay. So one way is basically the same as cannot skip. I don't know how many of you can want me to explain more about this point, or you are okay? Yeah, it's the same thing. So with that, let's take a break. Right now, my clock is 7:44. Let's come back again 5 minutes later. Let's come back at 7:50. Let's come back at 7:50.
So potassium doesn't have any properties?
Potassium, dude, I told you that stupid people, they have no issue.
Okay.
Think about this. It can only close and open. What can it do? You know, stupid people, they can only do simple things. Close and open, close and open. That's all. And stupid people, they are very slow. So they slow to open, slow to close. That's all they do, you know. Now you understand why I call potassium channel is stupid, okay? It doesn't matter. Don't worry about potassium channel. It's so stupid that it doesn't even feel a thing. Even when I call the potassium channel stupid, it doesn't hurt the feeling, okay? Because potassium channel does not have a brain. It cannot feel anything.
Got it.
And
Thank you.
Professor, is this all with one stimulus only?
Good question. Good question. Arnie asked this question. Very good question. When let's take the smart guys, smart sodium channel. If we stimulate the smart sodium channel here, of course it will open. After you stimulate here, I mean, when the channel is closed and then you stimulate the channel, then of course it will open. Then it will automatically go through this cycle. You don't need a stimulation here. You don't need another mild electric shock here to convert the open channel into inactive A. You also do not need another stimulus here to convert the inactive A into close. That's why I said that it is smart. It just do it by himself. Oh, where's the eraser? Do I have an eraser? How come they don't have an eraser here? Yeah, so once you open the voltage gated sodium channel, it will automatically cycle through open, inactivate, and then close. Similarly, after you give a mild electric shock to the neuron, then it opens the voltage gated potassium channel. Yes, from closing state, it will become open, but it will open slowly. For example, you stimulate it, you thought that when I stimulate, it will open, but after you stimulate it, it is still closed. You thought you start hitting on this potassium channel, hey, hitting it, how come you don't open? After you stimulate it, it may take maybe several seconds. Not several, actually it's only 1 or 2 milliseconds. It takes 1 millisecond. After the stimulation, it takes 1 millisecond for the potassium channel to open. And then after it opens, it lasts for maybe another millisecond before it closes. Yeah. But for sodium channel, after you stimulate it, it opens almost immediately. And then it will take about maybe half a millisecond, then you automatically go to inactivate.
Okay.
Half or 1 millisecond, yeah. So all these are automatic. Even the stupid potassium channel, after you stimulate it open, and then you don't do anything, it will take another millisecond to close by itself. You don't need cross here. You don't need any stimulation to close it. Okay. Any other question? Okay, let's start. Time's up. Let's start. Now, we learn about the three background information about action potential. First one is the threshold. Threshold is minus 55, which I just put it here tentatively. I don't want to write 55 here. Okay, the internet is too slow, too much lagging. Okay, so you know that this horizontal line that I drew, it is minus 55, the threshold. Now we will study the action potential part by part. So the flat line, we call it A. Part A. We break down action potential into different parts to study. So we have different part A. We call it part A is resting membrane potential. RMP. What do we have in resting membrane potential here? The value is minus 70. Millivolt. And then we have the leak channel open. What contributes the most to the RMP? Anyone knows? What contributes the most to RMP?
Potassium.
Oh, potassium, correct? The leak channel of potassium contribute the most. Good. So right now we are at minus 70, and how would you describe the opening of the leak channel of potassium? I'll give you, since you guys are bored, I'll give you a pull. Let me see. A. Sorry, no. Let me do another one. Okay, A, all lead channel of potassium open. B, most of the lead channel open. C, few potassium lead channel open. D, no potassium channel open. So A means all of them, 100%. B means most of them, a lot of them. C means a little bit. D means none of them open. Oh, someone chat. Let me see, what do you chat? Oh, you don't answer it here. I'll give you a poll. Come on, do the poll. It's fun. Let me see, 25 students voted so far. "26 students voted. Any more? 27 students voted. All right, forget about this. I'll show you the result. Oops, I shouldn't do this. It blocks my blocks my figure. Okay. All right, so correct answer is B. You guys are correct. So remember that the equilibrium potential of the leak channel is of the potassium is -90. At resting membrane potential -70, it is very close to the -90 EK. Because of it is very close to the equilibrium potential of potassium, then many of the leak channel for potassium are open, but not completely. All right. Now we go to part B, important part. So let's say we stimulate here. Then this is the part B. Ooh. This is part B. All right. B, come on. B. Ooh. Part B, I call this depolarization. Originally, I want you. It's okay. I don't want to. Originally, I want to do the speed dating thingy online using the break room. But it's okay. Just finish the lecture, then we can go to sleep. Depolarization. Yeah, you know how to spell it, right? I don't need to spell this. Depolarization. Okay. Now this is a good question. How? How do we trigger such a? How do we trigger this depolarization? Let me give a tips. We can do this by 3 methods. Anyone want to answer? What are the 3 methods we can trigger such a depolarization?
A strong electrical stimulus.
Correct, Amanda. Yes.
The temporal summation and spatial summation.
Brianna, correct. Good job. Yes, the 3 things I talk about. Instead of calling it the electric shock, instead of calling it mild electric shock, I only put electric shock. It has to be strong. Why? The electric shock has to be strong so that the graded potential will become very high, so high that you touch the threshold -55. Once it reaches the threshold -55 millivolt, then you will automatically transform to become action potential. Of course, we talk about spatial summation. And also temporal. I'll just put temp. I hope you don't mind. Don't mix it with temperature. It's not temperature, it's temporal. I didn't make this point when we talk about temporal and spatial summation. The truth is that in reality, in your body, in the real neuron, spatial summation and temporal summation, they occur simultaneous most of the time. Most of the time, they occur together. So it's not really, we only have one spatial summation, we only have one temporal summation. No, they usually occur simultaneously. When they occur simultaneously, it will maximize the chances of triggering action potential. So it is not just one factor, that will not one of the 3. No, usually all 3 they work together. so that you have a high chance to trigger the action potential. Any question so far? Is that cool? Most are open field. Can you repeat the question? Never mind. Melissa. Okay. All right. Okay. I'll check the chat. We'll see what you guys are doing. Okay. I'll continue with our lecture notes. So it is continue part B. Okay. You just keep writing under it. No, actually, I can erase this. Oops. Good job. All right. And I can continue stay with here. Just continue with your notebook. So what happened during the depolarization? This is the meat. Oh, I forgot to mention. Oh, in part A, the RMP. This is not too organized. Part A here. In part A here, does the do the smart channel and stupid channel open? Okay. You guys are too shy to answer. Let me see. Do the smart voltage gated sodium channel open in part A? In part A, I'm talking about part A, not part B. I go back to part A. In part A, do the smart voltage gated sodium channel open? Okay, 17 student, 21. In part A, resting membrane potential. Did the smart voltage gated sodium channel open? Interesting. Actually, many students, it's 53 versus 40. Okay, we'll have 12 students said yes, 12 students said, 16 students said no. Why? How come so many students said yes? The voltage gated sodium channel will open in part A, the resting membrane potential. Can someone volunteer to say, explain?
In equilibrium potential, it's plus 60, and then in RMP, it's minus 70, so they're far from each other.
Are you explaining no or explaining yes?
No.
You're explaining no. Okay, good.
But
okay.
I think a few of them are open.
Yes. So this is the voltage gated channel. Voltage gated meaning that the only way you can open them is to give them an electric shock, or you can change the membrane potential. But they are not like leak channel. Unlike leak channel. Okay. So we have to give them a shock in order to open it. So the answer should be no. So in the resting membrane potential, both the voltage gated sodium channel and the voltage gated potassium channel, both of them, they're closed during resting membrane potential. But when you give a shock here, what happened? Okay. Voltage gated. Sodium. I hate the lagging. Channel. Open. When the voltage greater sodium channel open, what will happen to the sodium ion? Can anyone tell me? Just unmute yourself and tell me your answer. No one wants to try.
Three sodiums will go from the outside of the cell to inside.
Excellent, Mariam. Excellent. Sodium ion goes in. Number 3. So when you have more sodium ions inside the cell, what will happen? What will be the membrane potential? What will happen to the membrane potential? Anyone want to try answering this question? Membrane, I hate it lagging. So slow. When we have more sodium ion inside the cell, what will happen to the membrane potential of the neuron? Okay, let me give you 2 choices. And then I just want someone to yell out the answer. Will the membrane potential increase, aka become more positive, or decrease, aka become more negative? Someone unmute them. Unmute yourself and answer this question.
It'll increase.
Correct. Thank you, Jonathan. Yes. Membrane potential increases or become more positive. Because you have the sodium ion, they are positively charged. Then when you have more positively charged ion inside the cell, of course, it will make the cell more positive. Any question about this point? Okay, number 4. I need to go to different slides. Number 4 is a little bit big. So remember that, okay, point number 1. Open. Oh, this is so slow. Maybe I should type, huh? What happened? Then let me see if I can type. And then, okay, good. Oh, yeah, save me some time. More sodium goes goes in. Okay, more sodium goes in. What happens when more sodium goes in? Then you have another one. Then membrane potential increases or become more positive. Remember, this is what we talk about the 3 point. Do you remember the 3 point? What happened? Point 1, point 2, point 3. These are basically the 3 point, but these 3 point, they actually do something very interesting. Then it goes back here. When you have more, when the membrane potential become more positive, that means it is getting closer to the what? ENA. When it is getting more closer to ENA, then you have more voltage gated sodium channel open. So this will just keep going. What do we call this? What do we call this phenomenon?
Positive feedback loop.
Oh, thank you, Jonathan. Good job, dude. Good job. This is impressive. You guys are still attentive. I'm happy. Positive back. Much better. I can do faster now. Okay, whatever. So what's so important about this one? When we go back here, you can see that part B, you see the rising. The stimulus here, it only gives it enough energy to pass the threshold. As soon as the amplitude of the greater membrane potential pass the threshold, what it means passing the threshold. When it passes the threshold, that means it has enough energy to trigger the positive feedback. When it triggers the positive feedback, it will continue to rise up by itself. You don't need to continue to stimulate to hopefully to get the temporal summation or whatever. You don't need that. You don't need to have a very, very large stimulus, because as soon as it passes the threshold line meaning that the cell has enough energy to trigger this positive feedback. If you only stimulate weakly so that you get the greater potential under the -55, what it means is that you do not have enough energy to trigger the positive feedback. So positive feedback is the one that brings the membrane potential to the peak. What is the peak? Until positive 30 millivolt. So this is the peak. Have I forgot something? Yes, I forgot something. Guess what I forgot? If you can guess what I forgot, I'll be very happy.
When does it inactivate and stop?
Desiree, that is too fast. You think ahead of time. You are very advanced. Let me give you tips. This is the tips. Blue. What does blue stand for?
Potassium.
Yes. The stupid channel. The thing about this, in part A, okay, remember in part A, both channels are closed. Part B, depolarization. Oh, wow. After the stimulation, after the electric shock, voltage gated sodium channel open. And then it actually triggered the positive feedback, rise all the way to the top, And then what about the stupid one? Stupid one is still closed. Okay. That's why I said it is slow to open, slow to close. Okay. Now this one, the peak here, I call this C. Peak is C. So have you noticed something? Let me ask you this question. If while I'm doing this, I want you to think about this. What happened? You said that how come the peak is at plus 30 instead of all the way to plus 60, which is the ENA? Because you know that, okay, we have the positive feedback loop, doing this. Do you feel dizzy now? Positive feedback loop. So that causes the sodium keep on opening. When you have more and more sodium channel open, theoretically it should make the sodium, it should bring the membrane potential go to plus 60, the ENA. But how come it stays at plus 30? What happened? I guess. Because sodium channel what? Smart. Why is it smart? NASA, come on, try it. Ani, try it.
Is it because it's inactive?
Excellent, Ani. Where are you? Are you on screen?
Yes.
Yeah, fist bump. Good job. Yes. Voltage gated sodium channel is fast, so that it is fast open, and guess what? Before it can reach minus 60, before it can reach the ENA plus 60, it already inactivate. So the voltage gated sodium channel inactivate at the peak because it is fast. It is so smart. It is so smart that it actually, it actually inactivate at the peak. What about our stupid one? Guess what? Record slow. Now the voltage gated potassium channel finally open. Why do I emphasize these 2 points here? They are actually the push-pull factor that causes the peak stays at plus 30 instead of the plus 60. As I said that, okay, the voltage gated sodium channel inactivate before the membrane potential can go to plus 60. That is like one of the push-pull factor. And you may call it push factor, okay? The pull factor is a potassium channel. When potassium channel open, what happened to the potassium ion? Anyone tell me? No one. So when potassium channel open, what will happen to the potassium ion? Potassium ion should
Go out of.
Yes, Miriam. Potassium ion will go out. When potassium ion go out, what will happen to the cell membrane potential, to the cell? Will it make it more positive? Okay. You guys don't like to talk, you know.
The cell inside is more negative?
Correct. Good job. Thank you, Brianna. Someone used the chat. Negative. Samantha Sanchez is correct. Oh, finally, I see your name. Yes, both Samantha and Brianna is correct. You make the cell more negative. That's why the membrane potential will not continue to increase to plus 60. By the time it is at plus 30, you have push-pull factor. Sodium channel inactivate, so you have no more positive ion going into the cell. When you don't have more sodium ion going to the cell stays at that level. But at the same time, you open potassium channel so that more positive potassium ion will leak out, will move out of the cell, making the cell more negative. So basically, this push-pull factor prevent the cell from reaching its so-called full potential. Maybe the full potential, which is plus 60. That's explain why, even though that you have a positive feedback loop for the sodium, it can never reach the full potential of plus 60. It can only go to plus 30 because of this push-pull factor. Is that clear? Can someone nod? Thank you. Annie, thank you. So Amanda and Jonathan, you guys nod. Thank you. So this is the push-pull factor to explain why the peak is at plus 30 instead of plus 60. Oops. D. What is D? D is, I call this repolarization. So Dn is around resting membrane potential. Is that clear? Dn is at the resting membrane potential. What is repolarization? All right. So what happens? Remember in part C, what happened in part C? Voltage-gated potassium channel open. I'll say more. And then you have more potassium ion goes out. And then membrane potential decrease. Remember, it is a repolarization. Decreases or becomes negative. Negative. Oops, this is not good. Let me spell that. Negative. Okay, let me see if I can show it here. Oh yeah, not good. But you know what I mean, right? You can read here. It is not too good. I better go back to school next time. Let me go back when you why? How come when the membrane potential decreases or becomes more negative, you have more voltage-gated potassium channel open? The reason is very simple. When it becomes more and more negative or less and less positive, that means it is getting closer and closer to the what?
Resting potential.
Okay, one said resting potential, the other one said something else. Because two students speak at the same time, I cannot hear it.
I said resting membrane potential.
Yeah, I think we both said resting potential.
Okay, so resting membrane potential is close to what other value? That will cause more voltage-gated potassium channel open.
Minus 90 millivolts.
Mariam, say it again. Can you repeat that?
Millivolts. Potassium.
What?
Minus 90 millivolts.
Correct. Minus 90. Correct. Good job. Yeah, the membrane become negative, become more and more negative because it is getting closer to EK. When the membrane potential get closer and closer to EK, then what happened? Then more and more voltage-gated potassium channel will open. So you see this circle again. What do we call this circle?
Positive feedback.
Correct answer. This is also called positive feedback. Good. Okay. One semester, I have a student very hardworking. I really like that. He or she, I forgot, actually read the textbook. I'm surprised someone read the textbook. So that student read the textbook and then asked me this question. He said that in the textbook, the part D that I show on the action potential graph here, the textbook does not call it positive feedback the textbook actually quite negative feedback. Why is that? How come your professor quite positive feedback, but the textbook quite negative feedback? How many of you read the textbook and noticed that? It's okay. Annie, you read it?
I didn't. I just have a guess.
Okay, try to guess why textbook quite negative feedback.
Is it because it's going opposite of depolarization or of that positive feedback loop?
Very close, very close. Let me give you a tips. I mentioned that resting membrane potential is the homeostasis of the neuron.
Yeah, so negative feedback brings your body back to homeostasis. So
Excellent, Brianna. Where are you? Are you on the screen?
yeah.
We can still do that, okay? Yes, excellent. This is exactly the reason textbook call it a negative feedback, because your textbook consider the resting memory potential as the homeostatic level of the neuron. In other words, the depolarization phase, part B, is actually the disturbance of the homeostasis. It's abnormal. And then, therefore, the repolarization, bringing back the membrane potential to the resting membrane potential, D part, is considered as negative feedback, because this is what normally negative feedback in our body do to bring back our body to the homeostasis. So I want you to distinguish the two. When your professor said that positive feedback, I'm talking about the stupid channel, the voltage-gated potassium channel. That is positive feedback. But when you talk about the membrane potential, then you may call it negative feedback. Does it make sense, the differences? Positive feedback, the stupid channel, voltage-gated potassium channel. Negative feedback, it is the membrane potential. That's the differences. Any question? Any question? Okay, you want to take an early break? You guys seem tired, even though you're at home. Let's take a longer break. Let's come back at 8:40. I'll give you 7 minutes. 7 minutes, okay.
Professor, I have a question. Will you
Yes.
be posting this lecture on Canvas?
Actually, this lecture is recorded.
Yeah.
Theoretically, you can come back here to watch it.
Okay, okay. Thank you.
Mhm. What about the Shernox area?
Yeah, I was wondering if anybody saw it because I think you can add notes, like your own notes over there, and I didn't know if anybody had done that.
I guess Shernox is for. I mean, can student do anything on it? Can you type anything on there? Is it
Yeah, let
something
me see
that
if I can.
student Shernox with other student? Oh, okay, it works. So Shernox is for student sharing with student. That's good. Okay, I hope everyone is back. It's 8:40 now. So let's move on. So this is part D. In part D, basically, I'm very lazy, as you know. Okay. All right. Okay. Try to be hardworking. Voltage gated sodium channel. What happened? It continued to inactivate. What about
When you mean inactivate, do you mean they close?
okay? Inactivate means the channel is open, but the ion cannot go through. Voltage gated potassium channel is continue to open. Thank you. Good. That's a good question, so that we can clarify. So basically, from C and D, the two channels, they are in the same state. Let me see if I can go back. Yes, this is the depolarization. Depolarization is very long. Yeah, okay. I erase the A part. The A part resting membrane potential is basically both channels are closed. Now let's go to E. No, it's faster now. The internet is sometimes slow, sometimes fast. The E part is tricky. Okay, it's just this tiny little bit. Oops, come on, come on. Tiny little bit. But this E part. So E part is basically the, well, take a guess the name of this. You should know the name.
Hyperpolarization.
Thank you, Molly and Desiree. Correct. That is what we call hyperpolarization. Thank you. Thank you. You guys are studying. Hyperpolarization. Good job. Good job. Hyperpolarization is less than minus 70 millivolt.
When you mean more than -70, do you mean that it's like -80 and -90, like?
Yeah, okay, this is what we call less than, not more than, okay? Less than, because the more negative it becomes, the smaller the number. So, yeah, it is the correct mathematical symbol. It is less than minus 70 millivolt. That means, as you said, it is like minus 80, minus 90, and so on and so forth.
Oh, okay.
So, why? You see.
Because the channels are open for too long, so there's too many potassium ions being pumped out.
Oh, excellent, Molly! Excellent! Are you on screen? No?
No, no, I'm in my son's.
Get my fist bump. Get my fist bump, dude. You are good. You are good. Okay. Excellent. Excellent. I got some very good stuff this semester. Why? Because voltage gated potassium channel, they are stupid, but due to political correctness, we don't call it stupid because the channel, they are slow to open and close. In other words, what will happen to the voltage gated potassium channel now? I guess what is the state? You know, the stupid channel only has two states, okay? You have 50%. I heard that right now all the casino in Vegas, they are all closed down. No one go to gamble. So they all closed down. So now you can imagine you are online gambling now. You have 50%. Do you buy red or black? Do you want to buy voltage gated potassium channel open or close? Come on. Amanda, you want to say something?
I said closed.
Close, okay. Remember, now hyperpolarization, it is undershoot. It is less than minus 7. That means it is minus 80.
Oh, it's open because more are leaving the cell, right?
Excellent! Oosh, oosh. Yes, it is still open. Oh, you guys are very good. I'm so happy this semester. What about sodium channel. The smart dude. The smart guy, because it is fast. What is the next state? You should know this answer. You can just go back to your lecture notes, then you can see what is the previous state. Brianna, close. Excellent. Now it is closed. Now you can see how stupid or how smart they are. Sodium channel is now closed, but potassium is still open. You know how slow, how stupid potassium channel is. And then part F, part F is the peak here. Peak, oops. The peak here is the deep, the deepest one, we call part F. Part F. What would be a good name to call it? We can just call it.
Period.
Oh, okay. Now you read ahead of time. I like that. You read ahead of time. We'll talk about refractory period later. We call this after hyperpolarization. I guess Molly, you have read the PDF file. You know, theoretically, when we're in the classroom, we need to do the speed dating activity so that you can read those PDF file. But we don't. It will be. We can theoretically do it online, but it will be very troublesome. That's why I skipped the reading. All of you should read those PDF file that I posted on Canvas. Those are for jigsaw, you know, those for activity. Those 3 PDF files, you should read them. But the way they use the term a little bit different from mine. Okay, after hyperpolarization, I refer to the deepest peak of it. What is the value of after hyperpolarization? Anyone knows?
Like the value is in like how many millivolts?
Yes, how many millivolt? Correct.
Anything less than 70, negative 70?
Okay.
Negative 90.
Shannon! Good job, dude. Good job, dude. Yes, negative 90. Why? You don't answer question in class, but now you answer 2 questions online because I told you that, you know, the online predator theory, you know, when you're at home, you feel safe, you feel comfortable, so you have a tendency to speak up more. Okay. Why? Because it is EK, equilibrium potential of potassium. When we are at EK, voltage gated potassium channel open. Now, let me ask you a question. See if you understand all this. How come sodium, how come the action potential never reach ENA, but it can reach EK? How come action potential can never reach ENA, but it reaches EK?
Isn't it because the sodium potassium pump?
Okay, you are one step ahead. You are one step ahead. I can tell that you did your reading, hardworking student. I like it. Unfortunately, you are not on the screen. You deserve a fist bump because you are hardworking. You do your reading, but you are one step ahead. But so this is not the reason. This is the next reason. The one step ahead. Okay, I'll ask this question again. You can repeat this answer. So Ani, want to try?
Is it because normally in a cell there's more potassium than there is sodium?
Okay, the amount of sodium potassium ion, it is the table that I told you not to memorize the number. So assume that you may assume they are about the same. You know, the highest is approximately 150 millimolar. Let me see. My question. Let me repeat my question. How come the action potential never reach ENA plus 60, but it reaches EK plus minus 90? So the first part of the question, basically we already talked about it. How come the action potential can never reach its true potential of plus 60, but how come it only reaches plus 30? Amanda?
Because we talked about the push-pull factor. That
Yes, the push-pull factor. What causes the push-pull factor? The push-pull factor, let's go back to the slides. See the push-pull factor.
Because the voltage-gated potassium channels are the pull factor.
Can someone repeat that? Two students speaking at the same time. I cannot hear.
The voltage-gated potassium channel is the pull factor, and then that's because when the potassium ions leak out, it becomes more negative, so it can't go all the way up to positive.
Okay, yes. What about sodium? What's the push factor?
Close back up when it gets to a certain, like at positive 30, it closes automatically.
Right. Sodium channel, they're smart, so they inactivate already. When they inactivate, then no more sodium ion can go in. That means the cell cannot become more and more positive. When you don't have more, when you cannot get more and more sodium inside the cell, you cannot become more and more positive, then you only stays at plus 30. So this is the first part of the question. Why we never reach ENA? Then how come we reach EK? How come we reach EK? Think about the push-pull factor. It is very similar.
Is it
What
because
does EK mean again?
the membrane always allows potassium, but it never allows sodium, like some of the time?
Okay, what about Molly? Molly, you want to try?
I was saying, what was EK mean again?
Okay, at least you guys try, and I'm happy. So, as I said, the action potential can never reach ENA because of the push-pull factor, which is very good. Amanda mentioned that. Main reason why, what is the push-pull factor? What causes the push-pull factor? Because of the smartness, the fast-acting sodium channel and the slow-acting of the potassium channel. Sodium channel is so fast, it inactivates. That's why it can never reach its true potential plus 60. Now, why it can reach minus 90? Because sodium is stupid and slow. It continues to open. It continues to open so that it can reach the true potential. In this case, it's EK minus 90 because it is slow to close. It continues to open until point F. But how come there's no push-pull factor? Because why there's no push-pull factor? Because the voltage-gated sodium channel is still closed. Then you may ask, how come it doesn't open? You said that it is fast, right? That means it is fast to open, fast to close, fast to inactivate. How come it doesn't open again? Well, how do you make the sodium channel open? You need to have a
stimulus.
Stimulus, Brianna, correct. You need to have a stimulus. You need to shock it. Because we don't give another shock, so sodium channel remain closed. Excellent. Brianna, this is a very important answer because it will bring to the next topic about refractory period. Okay. So at point F, you see that this should be in blue. This should be in blue. All voltage gated potassium channel is open, but the voltage gated sodium channel, they are closed. So of course you may think, oh, let's go to point G, right? No, we don't go to point G yet, but part G is here. This part is part G. Okay, the rising part. But before we talk about part G, there is an issue now. There's a very, very serious issue. We have to take care of it. What's the issue? Let me show you the issue. One, right now the membrane potential is equal to minus 90 millivolt, which is equal to EK which is okay, and it is not equal to minus 70 millivolt. It is not equal to resting membrane potential. Why is it an issue? What's the big deal? It's not an issue. Yes, it is an issue. Why? Because the cell is not in homeostasis. That's an issue. When the cell is not in homeostasis, that's an issue. Remember, we talked about it at the beginning of the semester. When we are not in homeostasis, we are sick. Okay. What is the second issue? Second issue. Second issue, inside of the cell, you have high sodium ion inside the cell. And outside of the cell, you have low, sorry about that. Okay, do not, right, okay. Outside you have high potassium ion. What does it mean? Meaning that you have, inside the cell, you have low potassium ion, and outside the cell, you have low sodium ion. You see the issue now. even the concentration gradient is totally reversed. It's totally reversed. And the membrane potential is not at -70, it's not resting membrane potential. And the concentration gradient totally messed up. So that is an issue. Why? We talked about this at the beginning. When your system is not at homeostasis, that means you're sick. And we don't want to keep the neuron at this state. EK means equilibrium potential of K plus, correct. So I'll look at the chat. Yes, let me type yes here. Yes. So correct. So how do we restore this? Molly, can you repeat one of your answers? See if you remember what you said. One of your answers.
The sodium potassium pump. This pump.
Good job. Excellent. Good job. This is impressive. Okay. Part G. Okay, I want to distinguish the two parts so that I hope you don't mind I change a little bit. I call this repolarization 1 here, part D. You just put a 1 at the behind. It doesn't cause you too much trouble. You just flip back your notebook. And then part G is repolarization 2. If you look at my definition, I gave you last week. Repolarization is basically going back to resting membrane potential, either from positive or negative. Why? Because sodium potassium pump. Remember we learned about this before the exam 1. It has something to do with gather rate. Remember sodium potassium pump? What kind of active transport is sodium potassium pump? Anyone remember? You only have 2 choices, primary or secondary.
Primary active transport.
Correct, Amanda. Primary active transport. Okay. What does it do? How many sodium it pumps, how many potassium it pumps, and also what is the direction of pumping the ion? Anyone knows?
Sodium go out and 2 potassium go in to the cell.
Yes, sodium.
It's 3 sodiums and 2 potassiums.
Excellent, you guys. I'm so happy. In this pandemic, everyone is depressing. You guys cheer me up, even though it's not my birthday. This is so impressive. You guys. Unfortunately, I don't think we will have time. We will have a chance to see each other again. Otherwise, I'll buy you some treat. Okay, and then let's take a look at the okay, here. The channel. What happened to the voltage-gated potassium channel, the stupid one? Take a guess. 50% chance. All right, you guys are sleeping.
Close.
Yes, Jonathan, thank you. Close. And then here. Voltage-gated sodium channel close. So there's something that I want to point out to you before we go to H. Oops. Let's take a look at the action potential, how it looks like. Unfortunately, I should have a laser pointer here, but the laser pointer is kind of slow. It has a lag. The red dot is my laser pointer. What happened is that if you look at the G part is the rising or repolarization of the membrane potential. Let me see, is it my Wesley student or you guys? Yeah, Glendale student asked me this good question. You guys asked me, previous Glendale student asked me that does the sodium potassium pump, what activates sodium potassium pump at the at part G? What activates sodium potassium pump at part G? So previous Glendale student asked me this question. How do you answer this? There's no electric shock, there's nothing, what activated? See, you guys ask good question. That's why, when I ask the question asked by your previous student, you guys have to think. Okay, let me tell you the answer since I see that many of you are thinking. That's all I need you to do, just to think about this. The truth is that sodium potassium pump, Jonathan, you want to try or?
Yeah, isn't the function of that pump to maintain the homeostasis?
Yes, but what activated?
What enzyme?
What activate to restore? Natalie Garrett, can you repeat your answer?
Will there be an enzyme that activates it?
Enzyme. That's a good guess. Sodium potassium pump is a membrane channel, membrane protein. He itself is also an enzyme. It actually requires sodium potassium ATPase. Remember, it has two names: sodium potassium pump or sodium potassium ATPase. So in itself, it is an enzyme that convert ATP into ADP. By converting ATP and ADP, it releases the energy stored in the covalent bond, and so that it will have energy to do active transport to pump free sodium from inside to outside, and to pump 2 potassium from outside to inside. So the question is, what activate? Actually, nothing activate. What do I mean nothing? It is continuously active. Why do I say it is continuously active? As long as we are alive, then the sodium potassium pump continues to work. Why? If you remember, what does sodium potassium pump require? It requires ATP. Where does the sodium potassium pump get the ATP from? From your mitochondria, cellular respiration. When we will make ATP cellular respiration? When we eat and when we are alive, then we will make ATP. So as long as we are alive, we make ATP, then sodium potassium pump continuously activate 24/7, 365. Does it make sense? It continues to activate 24/7, 365 as long as you are alive. If you are dead, of course you will die. It will stop working. The second question, you guys, former glanders, can ask very good question. Then they ask you, what about during the part B depolarization, part C, part D, part E, part F? What happened to the sodium potassium pump? How come we don't see any effect there? This is also very good. You guys are very good asking me this question. The truth is that during part B, part C, okay, I should say this way. During part A, part B, part C, part D, part E, part F, all these parts, the sodium potassium pump is active. It is always active. But how come you don't see the effect? Because part A, it is already in resting membrane potential. That's why you don't see any changes. Part B, remember what causes the sharp rise in the membrane potential? Anyone remember what causes the sharp rise in the depolarization in part B?
The strong electrical shock.
Yes, this is strong electric charge. Let me put it this way. What causes the rise of the membrane potential after the threshold?
Action potential?
Molly, say it louder.
Action potential?
Action potential. Okay. So what causes this part? I should indicate here. What causes this part?
The positive feedback loop.
Thank you, Jonathan. Yes, the positive feedback loop. The positive feedback loop is so strong that it actually overshadow or cover the function of the sodium potassium pump. That's why you don't see this. You don't see any changes. And also similarly here, the positive feedback loop of the potassium channel here overshadow, cover the function of the sodium potassium pump. That's why you don't see that. Okay, now this is point number one. Point number two is that I want you to pay attention to the slope. The slope of the part G here. And the slope of part B and the slope of part D. I don't know if you remember what we learned in the math, college math or elementary or high school math about slope. Slope is basically the rate. The slope is the rate. The slope of B and slope of D, they are, I would say, approximately the same value but opposite sign. One is positive slope, one is a negative slope. Okay, this is positive, this is the negative slope, but the value is about the same. It's very large, it's very steep. The slope is very steep. But here, this one, it is a positive slope, but the value is a very small. It's a small slope. It's a very shallow slope. So what I want to point it out to you is that by looking at the slope during part B and part D and part G, you can see that in part B, the slope is so high, meaning that the effect of the positive feedback is very large. Similarly, the slope on the part D tells us that the positive feedback of the potassium channel is also very strong. That's why the slope is very steep. But look at part G. The slope in the part G is very shallow, very shallow. That means the function or the effect of the sodium potassium pump is very weak. The function of the sodium potassium pump is very weak. yes, it will continuously do its job to restore the homeostasis, to restore the natural concentration inside and outside of the cell, but it takes time. It is slow. Okay, part H. Part H is basically, you probably guess it. Where is part H? Part H is basically this part. Oops. Oh, you're wrong color. I hate wrong color. Wrong color. Part H. It's in here. Okay, this is part H. Part H, well, it's the same RMP. Okay, I will do the typing faster. So I call it RMP, which is identical with part A. Again, it is basically everything restored back to the same level, minus 70 millivolt. We have leak channel of potassium. Channel of potassium. Basically, everything go back to part A. That's it. Okay, we are done with the action potential. Is there any question? Any question?
No.
Molly, you said something?
Oh yeah, I said no. No question.
Oh, okay, thank you. Thank you for responding. I appreciate that. Now you know how you know the structure of it, the so-called structure of the action potential. Now we have to go to the next one, the properties. We learn the structure, now we learn the properties. The properties of action potential. The first one is basically we already covered. It's like our background information, the threshold. The threshold is approximately equal to minus 55 millivolt. For that, I need to show you the screen. On 19. Ooh. All my annotation are here. Oh yeah, this is it. This is it. This is 8.19. Can you all see this? Can you all see figure 8.19 on the screen? Okay, some people not. Okay, thank you. Thank you for showing your thumb, Brianna. Thank you. So 8.19. Let me enlarge it so that I can annotate on it. All right. So you can see that the threshold, this is minus 55 here. So this is minus 55. The dashed line is the threshold minus 55. And the laser pointer doesn't work. Okay, these are, so here this is a stimulus. When you have a weak stimulus, so the y-axis is the stimulus intensity, or they call it stimulus strength. Basically, how strong you give the electric shock. Now this is a very mild electric shock at the beginning here, very weak. Then of course you get a small greater potential, and then we increase the stimulus strength, the stimulus intensity. Now you get a taller or higher greater potential. We call this graded response because it is a graded response because the amplitude of the membrane potential, the amplitude of the graded potential increases according to the stimulus strength. We give a stronger one, it is even stronger, higher. Now we call it threshold stimulus because now we increase to this strong. Then theoretically, the greater membrane potential should be like this. Oops. It should reach the threshold line. But as I said, as long as it reaches the threshold line, that means it gains enough energy to trigger the positive feedback loop of the sodium channel. That's why it will go continuously to shoot up like this. What I want to tell you is this part. This is very interesting. If we continue to increase the stimulus strength, theoretically our greater potential should be higher than the threshold, something like this. But we trigger the same. Action potential. The amplitude, they are all plus 30. It's not like, oh, I give a stronger stimulus, the action potential will become taller than plus 30. No. And if I continue to increase the strength, the stimulus strength, yes, theoretically the greater potential should be even taller. But as long as it passed the threshold line, it will give you the same action potential. In other words, no matter how strong you stimulate the action potential, no matter how strong you stimulate the neuron, as long as it's past the threshold line, it will give you the same action potential. What do we call this? We call this, see, let me go back. This is what we call all or none. I'll give a star here. My star doesn't look very impressive. I'll draw a big star here. Or AP, or action potential in any neuron have the same amplitude. What is the amplitude of the action potential? What is the peak value of action potential? Someone say, can you repeat that?
Positive 30.
Oh.
Excellent, Jonathan, positive 30. There you go. Agape, correct. Why don't you speak? You have the mic. Okay. So, let me ask you these two questions. See if you understand this. Okay. Stimulus strength. Stimulus strength is basically the same as a stimulus intensity, larger than threshold equal to some kind of amplitude. So no need to hurry. You may not understand what I'm doing. I'll explain it to you. So in case you write it down, then you have to change it, and you hate your professor, keep changing your lecture notes, you know. If it is larger than threshold equal to okay, I want participation. You know that I like this kind of crap. I always like you guys to write on the whiteboard. Okay, let me now I share. Okay, don't. Ooh, you see all your pointer? You can write on it, but before you write on it, let me write on it first. Okay, don't get too excited. You can all write on the whiteboard. You're so happy now. Okay, you can write on the whiteboard. Okay, if I okay, let me see. Let me put a star here. I said that I want to put a star here. I want to put a big star here. So this is important point. All action potential energy have the same amplitude. So the big star is here as well, making it very important. And then now what I want you to do, I want to fill in the blanks. If I increase the stimulus strength, so that the stimulus strength is larger than threshold, what will happen to the amplitude? Second question, if I decrease the stimulus strength so that it is still larger than threshold, what will be the amplitude? So on the whiteboard, any volunteer, you can write higher, same, lower. So it's like a multiple choice, higher, same, or lower. You can write or type. Someone has a cursor there. All right, now everyone wakes up. Oh, that's so funny. Someone draw something. Anyone can try. Someone said higher. Someone said same. Any more suggestion? You can disagree. Oh, someone handwrite same. Oh, someone type same. Someone handwrite same. Desiree like handwriting. Okay, good. The bottom one. Everyone agree with the same. Okay, good. Same. Okay, good. All right, now I have to shut you all down. Sorry. Get enough. Okay, thank you. Thank you for participation. Yes. Remember, usually after the speed dating thingy, we usually ask you to write on the whiteboard. Correct answer is the same. Good job. Correct answer on the top is also the same. So no matter how strong or how weak your stimulus strength is, as long as it passes the threshold, it will give you the same amplitude of the action potential. Any question? Yes, is it too simple? Okay, number 3. Number 3. Property number 3. Oh, property number 3 is the tough one. It's the tough one. Refractory period. Refractory period, we have 2 types. One is called absolute refractory period. One is called relative refractory period. You have to know them, unfortunately. Okay, let's go back to here. Our action potential. Okay, as you can see that I already indicated the absolute refractory period and the relative refractory period are the approximate location here. Let me see. So the absolute refractory period, basically it is from absolute from B to approximately D, from B to D. The relative starts from E to F. Okay, why? Okay, this is a good estimation. Okay. So in other words, the absolute refractory period is approximately 1 millisecond, and the relative refractory period is approximately 0.5 millisecond, approximately. What is absolute refractory period? What is the relative? Oops. The absolute refractory period, what it means is that during absolute refractory period, you cannot trigger another action potential. You may make a sentence like this: during absolute refractory period, you absolutely cannot trigger another action potential. That's why I call it absolute. That's only one action potential during the absolute refractory period. For relative refractory period, why do we call it relative? Because during relative refractory period, you can activate another action potential. But there's a catch. During relative refractory period, you can activate another action potential, but it takes a much stronger stimulus intensity, a much stronger electric shock, a much stronger stimulus strength. That's why we call it relative. Yes, you can trigger another action potential there, but it will take you stronger shock, stronger stimulus intensity. Okay, let me explain to you why. The difficulty is to understand why. I mean, I give you the definition, you can just memorize it. Okay, it's not a big deal to memorize it. Why is it so difficult to understand? Because it has something to do with what we talked about at the beginning. The smart voltage-gated sodium channel and the stupid voltage-gated potassium channel. I would say it is mainly has something to do with the smart voltage-gated sodium channel. The potassium channel doesn't do much. They are stupid, it doesn't do much. It is only the smart channel that has a lot of issue. It is the smart voltage-gated sodium channel that causes the absolute refractory period and the relative refractory period. Remember, you can flip your notebook back to the page that I talked about these two channels. When I talk about the voltage-gated sodium channel, I draw a triangle cycle. The close, open, inactive A, close, open, inactive A. It is because of this property that causes absolute refractory period. Why? During absolute refractory period, I said that it is part B to part D. So if you refer back to your note, what happened during part B? What happened during part B? The sodium channel.
Depolarization.
No, what happened to the sodium channel during depolarization? Desiree, continue.
It opens.
Yes.
So sodium goes
During part B, depolarization, sodium channel is opening. If you give an electric shock during part B, can you open more channel? No, they are already opening. That's why you cannot trigger another action potential during part B, which is the part of the absolute refractory period. Now, what about part C, the peak? What happened to the sodium channel? Someone just yell out the answer.
Still open.
Part
Inactive.
C, the peak. Jonathan is correct. Inactive. Inactive A. Inactive, yes. At the peak of the action potential, which is also during the absolute refractory period, now the sodium channel is inactive. It's inactivated, okay? When it is inactivated, can it reopen? Yes or no? Wait.
No.
Thank you, the three of you, Arnie, Brianna, Jonathan. When the voltage-gated sodium channel is inactivated, it cannot reopen. Why? Because it has to close first. It has to close first. That's why if you give an electric shock during part C, the peak, you cannot trigger another action potential. What about part D? I said that absolute refractory is part B to part D. What happened to the voltage-gated sodium channel during part D, repolarization 1? Inactive. Agape is correct. Inactive A, correct. So during part D, repolarization, sodium channel is still inactive A. Again, same reason, we cannot, if we give an electric shock, it does not open it because it has to go through the closing state first. That's why we call this time period absolute refractory period, because the sodium channel have not so-called reset yet. It has not reset. What do you mean reset? When it closed, then it can reopen. Because it has not reached the closing stage, then it cannot reopen. Then when it cannot reopen, we cannot trigger another depolarization. When we cannot trigger another depolarization, we cannot trigger another action potential. Does it make sense? Depolarization is basically the triggering of the action potential. If you don't have depolarization, you don't have action potential. That's why we call this period from B to D absolute refractory period. Anyone have any question? You can Now I'm open the public chat. You can type your question on the chat. I'm like a DJ. You can call. I can answer your question, or you can just unmute yourself and ask this question in public. Any question about absolute refractory period? Okay. If not, then let's go to the relative. How can we call it relative? Okay. Relative, that means we can trigger. Okay, relative refractory period has two parts. The definition has two parts, okay? First part is that during relative refractory period, we can trigger another action potential. This is the first half of the definition. The second half of the definition is that yes, we can trigger the action potential, but we need a stronger stimulus. We need a much stronger stimulus. Let's deal with the first part of the definition. We can trigger action potential, and why? Why we can trigger another action potential during relative refractory period. Let's take a look at part E. In part E, hyperpolarization, what happened to the sodium channel?
It's closed, so you would be able to trigger another one so that.
Excellent, Amanda and Agape. Yes, it is closed so that we can open it. We can reopen it. As soon as it's closed, then we can open it. That's the reason part E is part of the relative. What about part F after hyperpolarization? What happened to the sodium channel during part F?
It's closed.
Closed.
Yeah, it's closed. That's why it can still open. Oh, I make a mistake. I'm sorry. Your stupid professor make a mistake again. Okay, I want to change. That makes you pissed off. This is not part F. This is part G as well. This is actually part G. This is part G, not part F. From E to G. From E to G. I apologize. It should be from E to G. In part G, same reason. Sodium channel is also closed. That's why you can trigger another one. Okay, now, answer your question. No? Okay, that's fine. So, now we deal with the second part of the definition. Now you know the first half of the definition, why we can trigger another action potential during relative refractory period from part E to part G. Okay, not part F, sorry. From part E to part G, why we can trigger another one. Because it is closed, yes, Agape, correct. Because the sodium channel is closed. But then the second part of the definition, why does it need a stronger stimulus? Okay, why is it? Now we need to, Professor, you said that it is inactive, we cannot reopen it, right? Sodium channel is inactivated during part D and part C. Part C, the peak, part D, repolarization 1, okay? Part G is repolarization 2, so it is closed. So there are two repolarization. Part D is repolarization 1, part G is repolarization 2. In repolarization 1, part D, the sodium channel is inactivated. In part G, repolarization 2, sodium channel is closed. So that's the differences. Does it make sense? Okay, thank you, Agape. Okay, good. Now we have to explain why it takes a stronger stimulus to trigger action potential during the relative refractory period. Okay, let's remember that we have electrical stimulus here. We shock the neuron at this time so that we trigger the action potential. Okay. Assume. Okay. So this is stimulus S. This stimulus S, that means the stimulus strength or stimulus intensity is strong enough to reach the threshold line. so that it can trigger the positive feedback for the sodium channel. In other words, this stimulus S is strong enough to trigger action potential. Basically, that's the bottom line. What if I stimulate here? Same stimulus S. Then you will say, of course, you can trigger action potential. Yes, you can trigger an action potential here. It's a very disgusting action potential. Sorry about that. Yeah, you will trigger an action potential here. Why? Because when you stimulate in the new position, the greater membrane potential also touches the threshold line at minus 55. May I ask what's the differences between minus 55 and minus 70? So minus 70, the differences between them is approximately, let me do the math. The differences between them is approximately, what, 25?
15.
Is it 25? 15, okay, thank you. Okay, see, my math sucks. Sorry about that. The differences is approximately 15. The differences is approximately 15. What's the meaning of that? That means the amplitude. The amplitude of the greater potential is 15. Is that clear? The amplitude of the greater potential triggered by stimulus S is 15, so that it can reach the threshold and become action potential. Now everything makes sense. Okay, now your tricky professor stimulate here. So you first stimulate here. And then during the relative refractory period of the first action potential, you give a stimulation here at this point. S1 and S2, they're the same stimulus with the same stimulation strength. The only difference between S1 and S2 is that the time. We trigger S1 at maybe 1 millisecond. We trigger S2 at maybe 2.5 millisecond. But they have the same stimulus strength. When we have the same stimulus strength, what will happen? It will trigger a greater membrane potential of the same amplitude. What is the amplitude? Can anyone tell me what is the amplitude triggered by S15 stimulus? 15. Thank you, Molly. You're Molly, right?
Amanda.
I'm in full screen. I cannot see anyone. I'm in full screen mode. That's how I can draw accurately. Yes, this is 15. May I ask, can this greater potential become action potential?
No, because it hasn't reached the threshold line.
Correct. You understand why now. Why we call it relative refractory period. You need to trigger a stronger action potential here. You need to have a stronger stimulus, maybe a 2S. Okay, maybe you need a 2S stimulus to trigger a very, very high greater potential, so that it reaches the threshold line, then it will become the action potential. That's the reason. That's the reason why the second part of the definition of relative refractory period is that, yes, you can trigger an action potential during this time, but you need a stronger stimulus, because when you do this during the relative refractory period, the greater potential cannot touch the threshold line. You need a stronger stimulus to increase the height of the greater potential in order to reach the threshold line. Does it make sense? If it makes sense, not, oh yeah, thumb ups. Thank you, Amanda. Yeah, show me something that I know. Okay, good. Thank you. Okay, that's the end of today's lecture. We have one more property, but the last property is very simple. We can talk about this on Thursday. Is there any question you want to stay and if you want to stay and talk to me, I'm available to talk to you now. If not, then I'll see you on Thursday. You know how to log out? It is on top right hand corner. There's 3 dots. Then you can click on the 3 dot, and then there's a logout. Oh, you're welcome.
Dr. Lee, what should we do to plan for lab quizzes?
On Monday I went to the faculty meeting. I asked the whole department. They said that they don't know on Monday. So I'll ask them again on Wednesday. See if anyone got any idea.
So we might not have a quiz on Thursday.
I'm not so sure. Seriously, if we have quiz, we can do it online, but you need to install Pretoria. I don't know. I personally prefer to postpone the quiz because we don't even have a lab. What's the point of having a quiz if we don't have a lab? This is my take. But when I ask them tomorrow about the lab, and I'll ask them about the lab quiz as well. How can we? Artin asked me, Dr. Lee, how can we watch this again? I have no idea. I know it is recorded. Theoretically, if you go back to the conference in your course, then you should see that this conference becomes closed. It is a closed conference. But on the closed conference, you can click something. It should be recorded, then you can play it again on the canvas, theoretically. But let's see how it works. I won't delete it. Don't worry, I won't delete it. It's just a matter of playing around the canvas to see how it works. Any other question? Well, if not, you can go.
You'll keep us
Natalie?
updated. For me, though, I'll email you.
You can go to the upper right hand corner, your 3 dot there. Click the 3 dot on your upper right hand corner, then you can log out. Do you see that? The 3 dot on your upper right hand corner?
Okay, thank you. Okay, thank you, Doctor.
Yes, that's how you leave.
Professor?
Tali, yes?
Yeah, I couldn't get my webcam working, but I'm still here, don't worry.
It's okay, it's okay. I see that all 30 students are here.
Okay, good. I was wondering if you could just repeat that last part about the graded potential. They have the same magnitude of 15, but the one that starts in the after hyperpolarization, you said, what did you say again? Like, what's the difference?
Yeah, the difference is that, remember, S1 and S2, they are the same stimulus with the same stimulus strength. That means they have the same stimulus intensity. So if S1, S2, and S, all these 3, they can trigger action potential. That means the graded potential they trigger they should have the same amplitude, 15. So you have 15 amplitude, so they can reach the threshold line. When you do the same here, you also have 15 amplitude of 15 here, the green one. But then what happened is that because during this hyperpolarization, if you have 15 amplitude of the graded potential, it is not tall enough to reach the threshold line.
Mm-hmm.
When it is not tall enough to reach the threshold line, what do you do? Pauline?
Oh, you said it's not an action potential because it doesn't reach the minus
Threshold
65?
line. Yeah.
Oh, is that right? That it's not an
Yes.
action potential?
Yes. It is just a
Okay.
graded potential. So how do you
Okay,
make
got it.
it become a action potential?
Okay.
How do you make it become an action potential, Pauline?
Oh, you started at the negative 70 at
No. I force you to stimulate at the position S2. You must stimulate in the position S2. So how do you make action potential when you stimulate at S2?
Wait, like you
Pauline?
mean how do you make the stimulus like stronger? Like enough for it to reach?
Yes.
Oh, you mean those three things that we said earlier?
Yes. Excellent.
Oh, like the temporal
if
and
I force you to stimulate at S2, the only way you can do it is to increase the strength of the
Right,
stimulus, increase the intensity of stimulus, so that you get a higher or taller graded potential. When you get a higher or taller graded potential, then you can reach the threshold line. When you reach the threshold line, then you can become action potential. So that's why we call it relative refractory period. Yes, you can still trigger action potential here because sodium channel already closed, but it require a stronger stimulus in order to trigger action potential.
got it. Thank you.
You're welcome. Amanda, your question? All right. Bye. So all of you, okay, John?
Yeah,
Come on.
just to be clear, we're meeting again like this on Thursday, right?
Yeah, Thursday. I would say that I'm more than 90% sure that we will not have lab. We will probably have lecture, but I need to find out about the lab situation. I mean, if you don't have lab, yeah. What's your question?
Oh yeah, just like because like the website says like classes closed from March 16th through the 21st, so like that's why I'm just being 100%.
Well, yes. We will have lecture online. Forget about what they said. You know, we continue with the lecture. I don't know how you guys feel, but at least we can get something done tonight. I'm happy. But on Thursday, I will try to go to the school so that I'll use the high-speed internet in the school to teach. Hopefully, I will not have so much lag in terms of writing. Then we can talk faster instead of too slow. I don't know how you guys feel. I find that I talk too slow. I actually bore myself. Okay. So Thursday. Theoretically, we should also have lecture because I don't think they have figured out anything for the lab yet. But I promise you, I'll ask them Wednesday, tomorrow, and hopefully they'll get back to me. So any other question for the rest of the students? You are still here. Why? How come everyone is still here?
Hi, Professor. It's Vanessa. I was just wondering. Did you get my email? I messaged you on Canvas. I don't know if you've had a chance to read it. If you could just reply is all I'm asking. I don't know if you've read it.
Let me check Canvas. You sent me a message on Canvas?
I think so. Yeah, I sent you a message on Canvas.